What's up, everyone? Welcome back to the channel. Today, we'll be learning about limits. All right, let's get started. All right, so exactly what are limits? So I'm going to go draw a number line here real quick. All right, and you have the value a, and this is the x-axis actually. So what a limit tells us is if we choose values of x that get closer and closer to a from both sides, what does f of x approach? All right, how we would write that is limit as x approaches a of f of x equals L. All right, so as we choose values of x closer and closer to a, what does f of x approach? So if we wanted to find, I'm going to go erase this real quick. So let's choose an example. So limit as x approaches 1 of x minus 3. What does that equal? So what happens if you choose values of x really close to 1 and plug that into the function x minus 3? What does f of x approach? The answer to this question is 2. So in this case, you can evaluate the limit by directly plugging in a into f of x, but sometimes that does not work. But yeah, that's what limits are. Limits just basically tell us as we choose values of x that get arbitrarily close to a, super duper close to a, what does f of x approach? Okay, so the last slide we talked about two-sided limits. They're just written as limit as x approaches a of f of x equals L, right? And on the number line, it looks something like this. All right, and we're exploring what f of x approaches when we let x approach a from both the left-hand side and the right-hand side. But what if we only wanted to isolate one of the sides? What if we wanted to know what f of x approaches from the right-hand side, just completely excluding the left-hand side, or the other way around? So how would we do that? Well, these limits are called single-sided limits. So how would you notate that? Well, if you wanted to say that limit as x approaches a from the left-hand side, we would write a negative here of f of x equals L. So what this is showing us is we have a number line right here. All right, and this is the x-axis. So what does f of x approach as we choose values of x that get closer and closer to a from the left-hand side of the number line, all right? That's the left-hand limit, all right? This is the left-hand limit, all right? And this is the right-hand limit. All right, this is the right-hand limit. So what does this tell us? This tells us what f of x approaches when you get values of x closer and closer to a from the right-hand side only, all right? So for normal limits, it was for both sides, all right? But for this one, it's only from the right side, and then for this left-hand limit, it's only from the left side, okay? And one more important thing to know is for a two-sided limit to exist, you need the left-hand side limit and the right-hand side limit to equal each other. And that's a very important rule, okay? Okay, so we can use tables to help us evaluate limits. So we are given the task to, evaluate the limit as x approaches 4 of f of x, right? So what we can do is we can plug in super duper close values of x, like, values of x that are super duper close to 4, like 3.9, 3.99, 3.999, and see what f of x approaches, all right? So this will tell us the left-hand limit, but then obviously we have to do you have to check what our right-hand limit is, all right? So we can just plug in these numbers as well. Okay, so let's see. If we plug in 3.9 into f of x, what do you get? All right, you got 0.5312. That's what I got. All right, if you plug in 3.99 for x, what do you get? I got 0.5030. For x equals 3.999, I got 0.5003. All right, so for x equals 4.001, I got 0.5020. For 4.1, I got 0.5201. And then for 4.1, I got 0.71. Okay, so looking at this table, what do you think f of x approaches as you get values of x closer and closer to 4? Well, I think that from what the table is telling me, it would be pretty reasonable for us to conclude that f of x is approaching 0.5. All right, so that's what I'm going to say my limit is. And actually, the limit is 0.5. So yeah, the table allows us to evaluate limits, especially when they get really tricky, you know? Sometimes it's not really that clear. Okay, so let's go use some graphs to help evaluate some of our limits. So for this graph, we want to evaluate what the function approaches as x approaches 1, all right? So let's see, what is the left-hand side limit of this? So we're going to follow this graph and see what f(x) approaches as we approach 1 from the left-hand side. And we can see that this approaches 1, 1, all right? That f(x) approaches 1 as x approaches 1, okay? Let's take a look at the right side, okay? So let's see what f of x approaches from the right-hand side. And we can see that it's approaching 1, negative 2, all right? So from the left-hand side, the function's limit is 1, right? F of x approaches 1. But from the right-hand side, limit as x approaches 1, from the right-hand side is negative 2. And see how these two are not the same? So that means that this limit does not exist. In order for a two-sided limit to exist, both sides have to approach the same value. Let's take a look at this one. All right? Again, limit as x approaches 1 of f of x. So let's see. From the right-hand side, the function appears to be approaching 1, negative 2. All right? And from the left-hand side, if you take a look at the left-hand side, the function is also approaching 1, negative 2, right? So that means the limit as x approaches 1 of f of x equals negative 2 because it's approaching the same value from both sides. Okay, so what are infinite limits? An infinite limit is a type of limit where as you let x approach a certain value, the function grows like to infinity, or it goes down to negative infinity. So I'm gonna draw the function 1 over x, all right? This is the function 1 over x, all right? So if you wanted to describe the limit as 1 over x approaches 0 from the right-hand side, we would write limit as x approaches 0 from the right-hand side of 1 over x equals, well, you see that this function is going all the way up to infinity, right? So you would just say that limit as x approaches 0 from the right-hand side is just positive infinity, all right? And then you would also say that for the left-hand side limit, you would say that the limit as x approaches 0 from the left-hand side with this negative sign of 1 over x, that equals negative infinity. Because you see here that the function 1 over x is going all the way down to negative infinity. And this is going all the way up to positive infinity. All right? So because this is infinity and this is negative infinity, you would say that the limit as x approaches 0 of 1 over x doesn't exist because they're not equal, all right? However, if I decide to draw the graph 1 over x squared, all right, it looks something like this. So here, the right-hand side limit is positive infinity, and the left-hand side limit of 1 over x squared is negative infinity. So, sorry, it is still positive infinity. The limit as x approaches 0 from the left-hand side is also positive infinity. So you can say that the limit as x approaches 0, the limit as x approaches 0 of 1 over x squared equals infinity, because these two are the same, right? The function approaches infinity, positive infinity, from both the left-hand side and the right-hand side. And one more thing I wanted to add just before moving on is that whenever there's an infinite limit, there's a vertical asymptote. Like, a vertical asymptote is always going to happen whenever there is a infinite limit. Okay, so we just covered infinite limits, but now we have to cover limits at infinity. So limits at infinity are basically horizontal asymptotes, okay? So these are the type of limits that ask you the limit as x approaches infinity of f of x equals L. Like, what does f of x approach as we let x approach infinity? Many times, especially for polynomials and such, the function just approaches positive infinity or negative infinity. Okay? But for rational functions, especially where their degree of the numerator and the denominator are the same, or the degree of the denominator is greater than numerator, you will see that f of x actually converges to a certain value. Okay? So let's take a look at what the limit as x approaches infinity of x squared is, all right? So we know that x squared is just a parabola like this, right? It goes up, it comes from up, down, and up, right? So as we let x approach infinity, what do you think the function approaches? That function approaches infinity, okay? Now what if we ask limit as x approaches negative infinity of x squared? What do you think that approaches? That approaches also infinity, right? Because even as you let x go, like, get closer and closer to negative infinity, that value squared just becomes a positive number that's even greater. So that's the reason why the limit as x approaches infinity of x squared is infinity, and same thing, the limit as x approaches negative infinity of x squared is also infinity. If we take the limit of something like limit as x approaches infinity of 1 over x. All right, let's graph that one more time. This is the graph of 1 over x. I keep using 1 over x because it's just so simple. Okay, so just looking at the graph, what do you think the function approaches as you let x go to infinity? The function approaches 0. Okay, so we would say that the limit as x approaches infinity of 1 over x equals 0. And then knowing that, we can also say that there is a horizontal asymptote at y equals 0. Now why don't you go evaluate this limit? Limit as x approaches negative infinity of 1 over x. What do you think that equals? If you said 0, you'd be correct. So yeah, that's just limits at infinity. We're just looking at how the function behaves, as we let x approach infinity or as we let x approach negative infinity. If you wanted to evaluate this using a table, you could just use values of x that just get bigger and bigger and bigger. So you could use 10, then 100, then 1,000, then 10,000, and just see what f of x approaches if you wanted to evaluate what x approaches as what f(x) approaches as x approaches infinity using a table.